In today's session, we are going to learn about ping command. And the basic purpose of ping is to verify IP reachability. Ping, which stands for Packet Internet Grouper, is a very common method of troubleshooting the accessibility of devices. It uses two Internet Control Message Protocol (ICMP) basically. One is echo request or ICMP echo, and the next one is echo reply. This ICMP request means ICMP type 8 code 0, and the echo reply is type 0 code 0. Ping command also measures the amount of time it takes to receive the echo reply, which is basically your round trip timer in millisecond, of course. Ping command first sends an echo request packet to an address and then waits for a reply. Ping is successful only if the echo request gets to the destination and the destination is able to get an echo reply back to the source of the ping within a predefined time interval, which is by default 2 seconds in Cisco iOS, and this is basically your timeout time, right? Okay. In Cisco iOS implementation, there are two different ways to use this ping command. One is standard ping with limited options, and the next one is extended ping with some advanced options. So with extended ping command, we can set the DF bit inside an IP packet. Even we can use this record route feature of ping. We can modify or manipulate source interface, source IP address. We can set DSCP marking value, etc. So basically, the extended ping is used to perform a more advanced check of force reachability and network connectivity. Extended ping command works only at the privilege exit level, whereas normal or standard ping we can use either from the user mode or from the enable or privilege mode. In order to use this feature, enter ping at the command line and press enter. So here are some options. The very first in protocol, this is the default value like inside the bracket. So if you don't say anything, just hit on the enter key, which means this is the default option. IP, target IP address, repeat count. By default 5 packets are sent, but of course we can manipulate this value. Datagram size is 100 bytes, but 100 bytes means 20 bytes IP header. So this is your IP header, and inside ICMP 8 bytes is your ICMP header, and the rest 72 bytes data part only. So basically ICMP has 8 bytes header, IP has 20 bytes header, so which comes to 28 bytes. So actual data minus 28, right? The packet size is, let's say, 100 minus 28, that is 72 bytes is the actual data size. Timeout default is 2 seconds, and extended commands, if we want to use extended mode, then yes, right? Source IP, type of service, which is your differentiated service code point, DSCP marking, mainly used for the QS purpose, quality of service purpose. DF bit, by default this bit is not set, and DF bit means what? If let's say this is my router and this interface MTU is, let's say, 1400 bytes, right? And we have a packet of 1600 bytes. So interface M2 means we cannot send more than this. So basically, if the packet size exceeds M2, then this packet is broken down into small pieces or chopped off into small fragments, and these fragments are reassembled on other end, right? So this is the default behavior. Okay, if packet size exceeds M2, then packet is fragmented into small fragments. But if this DF bit, do not fragment bit, inside IP header is set, then fragmentation is not allowed, which means now if packet size exceeds M2 and DF bit is set, that is fragmentation is not allowed, then packet will not be sent out via this interface, right? Which means only packet either equal to M2 size lower than that will be sent out that specific interface. So that's the basic purpose of dear bit. The next one is validate reply data. Specify whether or not to validate the reply packet or not. Data pattern is mainly used for like troubleshooting, framing errors, and clocking problems over the serial interface or serial lines. Okay. Here there is another very important option here, which is record route feature. Record route basically uses IP option field inside IP header. And for what purpose? So basically, uh, it displays the address or addresses of the hops the packet goes through, which means if R1 takes this path to reach here, R1, R2, and R3, and R3 takes another path to reach R1, right? Which is basically asymmetric routing. So we cannot figure out this by using trace route command, because trace route means कि from here my local router or to the source to the destination. So as per the routing table of this R1, trace route displays outputs what my routing table says, right? What my routing table takes the path, whether via R2 or via R4. But how destination is routing to me, what destination routing table says, of course there is no way to figure out this unless and until we don't have access of destination router. So if we have access, either telnet or SSH access of this router, of course we can trace route back to the R1. But what would happen if we don't have access to R3? So by using simply trace route command only we can trace the route from source to the destination, but which is basically from the perspective of source router, but we cannot figure out return path, right? So again this option is very useful for that purpose, record route option of extended ping command. And how to use this I will just explain after some time. And the next option is sweep ranges of sizes. So if let's say we want to send out ICMP echo packet of different sizes, like starting from 100 bytes to 200 bytes, so we can use this option, sweep range of sizes. Okay, so to demonstrate this, let me take a very basic topology of two routers only. So let's say we have two routers, R1 and R2, and from here R1, let's say if I say I want to ping 12.0.0.2 just to verify IP reachability between these two routers, right? Even we can use here host name instead of IP address, but this host name first resolves to IP address, and then this packet is IP packet is encapsulated inside Ethernet header, and then finally it is sent out. So for this host name to IP resolution, we need to have either DNS or maybe the host file sort of thing under this router. So straight away let's use this IP address instead of host name to test or verify IP reachability between these two routers. And even we are going to capture out packet just going through this link from R1 to R2. So let's start testing this. So R1 F0/0 interface, IP address 12.0.0.1 to 550.0.0. This is with the default mask. Similarly R2, another router. Here we have the same interface F0/0 which connects to R1, and IP address 12.0.0.2 with the default mask, and bring up the interface with no shutdown command. Let me turn off logging to console and enable logging buffer, right? And another command is debug IP packet detail and debug R. Now just execute this command, ping command, and ping and then destination IP address which is 12.0.0.2. Okay. So the moment I type this command 12.0.0.2, what R1 will do, R1 will check his ARP cache table, right? Do I know the Ethernet or layer 2 address of this IP, which is MAC address, like hexadecimal value, right? which is physical address or MAC address, layer 2 address, because this IP packet has to be encapsulated inside Ethernet header, right? Ethernet header or layer 2 header, and this is your error checking like FCS sort of thing. And this Ethernet header means source MAC address, which is sender MAC address, R1 MAC address of course, and destination MAC address, R2 fast Ethernet MAC address, and then ether type field, right? So ether type field is mainly used to just like to tell which upper layer protocol we are going to use. So if it is like 0x and then something like 0800 sort of thing, which means the next one is IPv4. So source MAC of course R2 already knows its MAC address, but what about the destination MAC? So if of course if this is going to be the very first packet, so this R cache table means blank, so R1 will not have MAC address of R2. So to obtain destination MAC address, what R1 will do, will send R broadcast message who is 12002, right? Tell your MAC. In response, R2 will send out R reply message, which is R response message. You are looking for my MAC address, and this is my hardware address or MAC address. Once layer 3 address, which is IP address, it is resolved to layer 2 address, which is MAC address, then the actual packet means this your this IP packet, this actual packet is encapsulated inside Ethernet header, which is your layer 2 header, and then finally it sends out ICMP packets. And basically this R1 R2. So basically by default in Cisco iOS there are total 5 ICMP echo packets of 100 byte size are sent, and the default timeout is 2 seconds. So maximum this sender will wait for 2 seconds for the response back by the destination. Within 2 seconds, if it R1 doesn't get any response, then that means timeout, 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 right? Timeout sort of thing. And if there is proper response, then yes, some response messages. So let's verify like this IP reachability by just putting down here ping command, ping 12002, and before that let me debug. So sorry, I believe already we have debugging on. Yes. So 12002, and before that let me check is R cache table. So since already there is R entry here, so let me clear out this R cache table. So clear R, sorry, and let me shut down and bring up this interface again. Sometime this clear R command never works, so better to shut down and bring up this interface. Some protocol is running on, so clear this out. F0/0 shut down. Okay, even the R cache table show R, nothing is here. Similarly shut down this interface as well. We are going to bring up this interface with the no shutdown command. Here again on R1 no shutdown command. Okay, some other protocol might be running behind the scene. So already since it has of course if it already knows what is the MAC address or layer 2 address of this destination, like as it knows here. So of course though now there is no need to send out our broadcast message, because already it has like IP address corresponding to MAC address. So this is layer 2 address, this is layer 3 address. So even this R cache table has a specific entry, so some protocol might be running behind. So with the help of that protocol the moment we clear this arc cache table, immediately it relearns the arc cache table. So no issue. Go ahead and just type in here ping command, ping 12002. So now the response must be 100% exactly, because already it knows the destination MAC address. So out of 5 packets, 5 were responded in a timely fashion. So there were 5 packets, 1, 2, 3, 4 and 5, right? So R1 uh, sent 5 packets and all the 5 packets were responded back, and the average time was 104 millisecond, the maximum was 136 and the minimum 80 millisecond, maximum, average and minimum, and it is what, round trip timer. So basically average time, like R1 sends R request and R reply message, right? Sorry, ICMP request and ICMP reply message, not R, I'm so sorry. So is a round trip timer, right? Average time in millisecond, and the timeout, default timeout, 2 seconds. ICMP equals, which means type 8 code 0, destination 12002, packet size was 100 bytes. Even if you want to change these parameters, so there are two ways. In very basics, even we can use uh, some options with the ping command. For example, if you say ping 12002, put a question mark here, so a lot of options are here. For example, you want to increase the size of this packet 1600 bytes, perfect, right? Behind the scene, what must be happening here, okay, this 1600, because the interface MTU, let me, the interface MTU, right, this is what, 1500 bytes, right? Only 1500 bytes. And if even if I say ping 12002 size 1600 or 1700, no issue at all. We are getting proper response from the R2. Why? Because DF bit is by default not set, which means fragmentation is allowed. So this packet of like 1600 bytes must have been chopped up into small fragments. What if I say I want to ping 1600 bytes, but please do not fragment this IP packet? Now, no response at all, right? Because this packet requires fragmentation, and fragment bit, do not fragment bit was set, which is ICMP type 3 and code 4, which is destination unreachable. Why? The error code is 4, which means fragmentation needed and do not fragment was set. Alright, let's say you want to use some other options, like you want to increase number of packets from default 5 to 15, then the command is repeat 15. So now 15 packets, okay. Let's say you want to say ping 12002 and the default time 2 seconds, well 0 second, but do not wait for, right? Just blindly keep on sending out ICMP packets, and let's say repeat packet 100, repeat 100, or maybe 200. So 200 packets, right? Without waiting for timeout period, which is 2 seconds, which was in fact by default 2 seconds. So straight away sending out echo request messages without waiting for any response, and as a result of this, success rate is 0%, right? Because we are not waiting for the reply message. So because timeout 0 second instead of default 2 seconds. So we have very good options here, like if we want to increase number of packet, then the repeat command. You want to increase the size, then size command. You want to set the timeout, then the timeout command, and even we can use all these parameters all together, right? Different options: repeat, size, timeout, DF bit even. And if you want to break this, then Control Shift and 6 from your keyboard. But it's all about the standard ping command with different options, with different features. And let me open the Washa capture. Washa capture between R1 and R2, if there is any. Yes, so we have A lot of messages here. Is there any ARP message? Yes, we have some ARP messages. And what about ICMP? So ICMP message. Okay, perfect. So let me open the very first one, this, and to show you different options. Okay, IP, Ethernet. Perfect. All right. So here we have uh, Ethernet header. Where it is? Okay. Ethernet header. This is what? Your layer 2 header. This is layer 2 header. Ethernet header. Ethernet header means source MAC address, destination MAC address, and this ether type field, which is 0x0800, means the next layer is what this Ethernet header has to say. The next layer is IP version 4, right? So from here Ethernet header we come across the next layer is IPv4, and then after here we have ICMP, right? Inside IPv4 there is another important parameter, which is protocol number. Ethernet header, ether type field is there, layer 4 header, IPv4 header, protocol number. So if the protocol number is 1, which means the next upper layer protocol is ICMP. If it is 6, then the next layer upper layer protocol, transportation protocol, TCP. 17 means the next upper layer protocol is UDP. 47 means GRE header. If it is 88, which means ERGRP. 89 OSPF, right, etc. So this protocol number field is again very important. From the protocol number field we come to know which transportation layer protocol or upper layer protocol has been used. For example, if let's say it is telnet packet or telnet data, so telnet means transportation, it uses TCP, which means inside IPv4 header the protocol number would be 6. When we open, then further if we further go to upper layer, which is TCP header, so inside TCP header there would be like destination port number 23. So destination port number 23 means application layer protocol is telnet, right? So from outermost layer, this is your entire packet. From outermost layer, for example, if it is your Ethernet header, inside Ethernet header there is ether type field to tell which upper layer protocol or network layer protocol has been encapsulated inside Ethernet header. So if it is 0x800 means IPv4. Inside IP header, protocol number field tell us which upper layer protocol or transportation protocol has been used, whether it's TCP, UDP, GRE, OSPF, ESERP, etc. And from port number, which would be inside layer 4 header, so if it is TCP or UDP, right, layer 4, then there is another field here, which is port number, destination port. From destination port we come to know about application layer protocol, upper layer protocol, right? So basically here we have layer 2 header, which is Ethernet, and from here to here layer 3 header, that is IP header, basically IP version 4, and the length is 20 bytes. DSCP marking, differentiated service code point, used in QS, or basically it is type of service field TOS, which is 1 byte in length. Okay, and the total packet length 100 bytes, but as I told you 100 bytes is the total size, right? But 20 bytes IP header, 8 bytes ICMP header. So you got my point. Now the data is what? 100 minus 28, right? These two are added together, 20 plus 8, so 28, and then total 100 bytes minus 72, sorry, 100 minus 22, sorry, 100 minus 28, which comes to 72 bytes only. Perfect. Okay, so actual data is 72 bytes. Fragment bit was not set and TTL, time to live, that is number of hops, right? So TTL means what? If we send a packet from this network by setting up TTL value, let's say 2, which means this packet can reach up to maximum 2 hops. 2 hops means, and any layer 3 device which is in routing mode uh, by default is considered to be one hop by default, because there is some exception to this. There are some firewall devices like Cisco SA firewall they do not decrement TTL value. So of course whenever we just execute trace route or any other command, so we never come to know like there is some layer 3 device in between. So it's just only exception. Otherwise all layer 3 devices, which means routing capable devices, are considered to be one hop. So here it was like the TTL, time to leave, fragment bit, ICMP. This is what protocol number is. Is it very important protocol number? This is one, means the next layer is upper layer, means this is what? ICMP. So it is ICMP. ICMP has like if some ICMP header means type and then code, checksum and some other data. It's all like ICMP header means total 8 bytes, right? Type field is 1 byte, code field 1 byte, 2 byte is here. So 2 plus 1, and then finally other data part is again 4 bytes. This type field is very important, ICMP type, right? And 8 bits means maximum we can have 2 raised to the power 8, which is 256, or 0 to 255, right? For example, type 8 with code 0 is your echo request, right? Type 0 code 0 echo reply. Type 3 again is very important. This is destination unreachable with different code like 0. Code 0 is destination net unreachable. Then we have code 1. Code 1 means host unreachable. Then we have code 2, that is protocol unreachable. Code 3 is port unreachable. Similarly, like we have different even code 4 is fragmentation needed but do not fragment bit is set. Code 11 even is very important. Code 11, right? Destination network unreachable. So we have different types, different codes, right? So these two parameters, types and code inside ISMP header again is very important. And here if you can see here, so let me choose different color for this. So here we have type, code and checksum, right? These are what ICMP header part. And if I scroll down further, then the data is hardly 72 bytes. Yes, it is. So here we have 72 bytes data field, right? So 72 bytes out of 100 bytes. Okay. So coming back to the topology, let's say you want to use extended command. So ping enter protocol target IP address, let's say 12002, repeat count, let's say 1 packet or 2 packet, datagram size, let's say 1400, timeout maybe 1, extended command, yes, source IP address 12001, type of service dear bit no, validity no, data part nothing, not at all. Okay, so is the way like how to use the extended ping command, but let's do some manipulation here. Let me use this command in very different way. Let's say the MQ size of this R2 is 1480 bytes, right? Okay, 1480 bytes. Alright, M2 size. I'm sitting here on R1. I don't know the M2 of R2. My M2 is the default of Ethernet, which is of course 1500 bytes. So of course my M2 size is 1500 bytes, but I don't know the M2 size of on the router, and basically I do not have access to this R2. So I'm sitting here only on R1, and I want to know M2 of R2. What is the M2 size of R2? So what I'm going to do now, I'm going to use extended ping command in a very different way. What I will do, from here I will use extended ping command with the ping sweep option. Let's say I'm going to send 1450 to 1500 packet length size, starting with 1450 bytes and maximum 1500, right? So which means the very first packet 1450, then the next one 1451, then the next one 1452, 1453, up to 1500, and only one packet of one packet length size, only one packet. Default is 5, right? So what I'll be doing, I'll be sending only one packet of 1450 bytes, the next one 1451, the next one 1452, and so on. I will keep on just increasing the packet size from 1450 to 1500 bytes, and only one packet of each size. And at the same time, dear bit, do not fragment bit inside the IP header will be set, which means fragmentation will not be allowed, right? So what R1 will do, R1 will send the very first packet 1450 with DF bit. If we get the response, then the next packet 1451 DF bit, and so on. So let's say if we were able to get the response of initial 5 packets, which means 1450, 1451, 1452, 1453, 1454, and then continuous RTO, which means the M2 is 1454 bytes only, right? Let's do the implementation here. So let me change the M2 size of R2 interface to any value. Let's say IP M2U 1460 bytes. Okay, 1460. I'm sitting here on R1. I don't know the M2 size of R2, and what exactly I have been looking for to find out M2 of R2, my next hop router. So I'm going to use extended ping command. Ping, enter. Protocol target IP address, right? 2, and what is the repeat count? Repeat count is 1, not 5 here. Okay, so because the default is what? Default is 5, total 5 packets, but what I'm going to do here, I'm going to send only one packet, right? Because further I'll be using this option, ping sweep option, right? I'll put down a range here like 1450 to 1500 bytes. So only one packet of one size. Otherwise, if I say like just do the ping sweep from 1450 to 1500, which means 5 packets of 1450, then the next 5 packets of 1451, then the next 5 packets of 1452. So needless to send out so many packets here. So better to just say only one packet. Okay. Now next, enter. Datagram size is perfect, like let it be default value 100 bytes. Timeout, no issue. And here say yes, I want to use extended command. Source address or interface default, which is of course 12001. Type of service, we are not going to use this, and yes, we want to use here set DF bit in IP header. So I am going to say yes, please go ahead, use this DF bit. set the df bit inside IP header, and this would be 1 instead of 0. Validity no, data pattern no, no record route yes. I want to use this option again, sweep range of sizes, and the minimum 1450, maximum 1500. Perfect. And just interval is default, and see here. Basically, we got the response of 1450, 1451, 1452, 1453, 1454, 1455, 1456, 7, 8, 9, and 10, right? 1460. And then after continuous RTOs, because the next one would be 1461 RTO, 1462 RTO, 1463 again RTO, 1464 RTO, right? So in this way we can find out MTU of Control Shift 6. This is the only way to break down this. Okay. Even here you can send key out of 23 and only 11 packets were responded, right? Even you can count this like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, and including this like 1450 is also included, which means maximum MTU is 1460. So it's another use case of extended ping command, which is very useful. And to further demonstrate this, let me take another topology, and here, right? So there are total 5 routers, 1, 2, 3, 4, 5, and uh, we want to configure asymmetric routing in an R1, R2, R3, 5. What exactly I have been looking for? Let's say uh, at very first place, after assigning IPs to these interfaces, just configure any routing protocol, let's say OSPF or any other protocol. Advertise all the interfaces inside this OSPF, and definitely if all the links, like link between R1 and R5, R5 and R4, and every all the links in fact are of same bandwidth, so definitely R would take this path as the best path, R1, R5, and R4, and R5, R4 also will take the same path, use the same as the returning path, right? So this is basically symmetric routing. Symmetric means ki R1 is taking the same path as R4 is taking, right, via R5. But let's say what we want to manipulate here, we want to configure R4 in such a way that R4 should take this path, right? So this one R4, then R3, then R2, and then finally R1, which is asymmetric routing. R1 takes path via R4, R5, and R4 takes path via R3, R2, and like this, R4, then R3, R2, and then R1, right? So what we'll be doing here, we will just manipulate, we'll just play around OSPF cost value so that R4 should take this path as the best path, and then further we'll use this extended ping command, uh, like record route option of extended ping command, to know like how this all happening, which path R4 is going to come back to R1 and which path R1 is going to take, because trace route command won't be able to do that, because by using trace route command what would come to know okay, how R1 is routing to this R4 only, right? Which means R1 loop back to R4 loop back. We would never come to know like how R4 is routing back to me, that is R1. So R1 always just uh, track or trace the route from the perspective of routing table of this R1, not from the routing table of R4. So if I do not have access to this R4 router, destination router, so we won't be able to just like find out the returning path what R4 will be taking to reach R1. So to demonstrate this, just configure all routers first, R1, R2, R3, R4, and R5, and a routing protocol, and then some symmetric routing, and then we are going to use extended ping command. Okay, so let me open console of our routers. So R1 and R2 already. So let me take a loopback address here, 111 and then /32, and on the interface f0/1, and f0/1 connects to, as per the, sorry, uh, let me check this side by side. So f0/0 is 15.0.0.1 255, sorry, 0.0.0, and no shutdown, and then router OSPF any process number, and of course these like OSPF configuration is not relevant here, so I'm not going to discuss this OSPF and all that. Basically we are focusing on the extended ping option, so it's not important. So R2, and let me set the M2 size to its default value, as this OSPF is going to create problem. So if someone is comfortable with routing part, so he must be knowing that this M2 size is compared during OSPF X start state. So if it is not same on both the ends, so OSPF will get stuck in X start state. So now configure F0/1 interface of R2, IP address 23.0.0.2.255.0.0.0, no shutdown, and then OSPF process ID 2, and wildcard mask or subnet mask. iOS is capable of converting that. So, and the next router here is R5. So let me configure R5 first. F0/0 interface, IP address 15.0.0.5. The next one is F0/1, and sorry, F0/1, and this goes to 5, sorry, R4 slash, and then OSPF configuration. So area 0, and here comes another routers, these two routers, so R3 and R4. R3, so F0/0 23.0.0.3 to 55.0.0.0, shutdown command, and then F0/1 goes to R4. So OSPF configuration, router OSPF, some process number here, and then network address and area number, which is 0, and finally R4. So F0/0 interface goes to 3. So default mask, where is the problem? MBO IP address, so it might be because of this, yes, and then no shutdown command, F0/1, and this 45.0.0.4, bring up the interface with the loop back, which is 444.255.255.255.255, router OSPF 4, network 0.0.0. Okay, loop back, yes, perfect. Show IP OSPF never, coming up. Okay. So now, in the meantime, let me open this screen. So first we'll execute trace route command from R1 to just find out the path to reach from loopback 111 to 555, right? There are two loopback IPs. So I believe this it took this path R1 to R5 and then R5 to R4. So straight away the very first hop would be like 15005 and the next hop address would be 45004, right? Only two hop counts. Okay, and even from R4 if we execute the same command trace route tracing back to this 111, so R4 will take the same path R4 to R5 and then finally R1. But since we are looking for asymmetric routing, that means we need to manipulate OSPF cost, we need to increase cost of this link, right, as compared to this, so that R4 should prefer this path as the best path for returning traffic, which means R4 to R3, then R3 to R2, and then R2 back to R1. Okay, so in the meantime, now open R4 routing table, show IP route. Okay, and show IP OSPF neighbor. So if we trace route from R4 to R1, so via R5, sorry, command syntax was wrong. So via R5, perfect. What about R1? So we want to trace route to 444, 454. So as expected, it had been respected. So trace route output is of course key as it would have been expected. So now we want to change the base path from R4 to R1. So on R4, so IP OSPF show IP route for R1 cost is here 21, okay, via R5, and R5 interface is this F0/1. So F0/1. So let me increase OSPF cost so that this should not be preferred anymore. So what next now? IP route. So if we trace route to R1 from R4, so it's taking first hop as R3, R2 and then R1, right? R3, R2 and then R1. So here it is. Okay, so R4 is taking this path. So R4 is taking R3, then R2 and R1. And what about R1? R1 is taking different path via R5. So if we are here from R1, this trace route to R1, so it's via R5, right? And from R4 via R3. Now the big question is, what if we do not have access to this R4, right? At this point of time, since we are accessing both the routers altogether like R1 and R4, so definitely we know like what path R4 is going to take to reach 111 from 555. But what if we have only access to R1, right? So from R1 perspective, if I run this command trace route 444 sourcing with 111, so it's taking 5 and then 4, right? We'll never come to know R4 routing table perspective. Okay, how R4 would be routing back to me. But what about this extended ping command? Use this ping, enter, protocol, target IP address 444, repeat count, let it be 5, no issue, or maybe only one packet, not a big deal, maybe only one packet, no issue, two packet or one or whatever, take one only, sorry. Datagram size, timeout, extended, yes, source address 1111, sourcing with the loopback IP. No type of service there, with nothing is not important, not important here. And yes, we want to use record route. Verbose is the default option, right? Verbose means we'll have the output here. This is the maximum value, 9 hops. So now the default option is record route along with the verbose option. Sweep brains, no, not at all, not at all. Yes, perfect. Now analyze this output here. What this output says here, let me check my pen here. Key, it was 15001, 15001, right? And then 45005, so it is your R1, then R5, and here R4. 15001 means this interface, exit interface, then 45005, this exit interface, right? Yeah, and this, and then 444 reached here, loopback IP address 444, coming back to R3. So R3 means 34004, this interface, and then R3 to R2, and then R1. R2 means this 23003 here, and then 12002, and then finally 111. This is what record route options. Record route option means we now know the complete path. R1 goes this way, R1 to R5, R4, then coming back via this, right? This is another great use of this record route option. And if we have captured packet across this path, let me open this Wireshark. Yes, and we were capturing here, and just let me check the ICMP packets only. ICMP packet time to leak exceeded, it is just press route command, and here it is last packet R1 to R4, R1 to R4. Let me minimize this and scroll down a little bit. IP header, only we are concerned with the IP header, and see here, great. Okay, so here we have record option field here, option field, right, inside IP header, and here record route option, right? Even some firewalls, they do not allow IP packet with the record route option or anything inside IP option, which is known as, you know, like sanity check, IP sanity check, like sanity check, anti-spoofing, anti-spoofing. So like checkpoint firewall, even other firewalls, what they do perform sanity check and anti-spoofing before like checking ACL and other parameters. So of course it could create some sort of problem. But here we have this IP option field, and inside this IP header field is all blank, right? Blank, 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 nothing here, nothing here. Why? Because this is echo request packet sourcing with, see here, sourcing with this 111 and then destined to 4444, right? So packet from R1 to R4, because this is captured between, where this is captured between, we have captured at 2 point of time, one here, we have captured here, right, onto this interface here captured. So the packet is sent with the IP option, but the blank IP option, that is 0000000, right? But will come back via this, like R4, then R3, then R3 to R1, and then finally R2 to R1. And we have captured here across this segment as well. So let me open that Wireshark capture. If we could retrieve some information from there, let me check what is inside the IP option field. The last one, reply message, reply exactly this one, the last one, sourcing from 444 and coming back to me like R1. So this is my reply option. Coming back to this record route option, and here, yes, here we have, see here. So like from R1 to R5 we have captured here like Wireshark capture with the record route option 0000, and then the packet went to R4, R4 sent back to R3, R3 to R2, and then R2 to R1 like this, and we have captured here again. So coming back, like which is the reply packet sourcing from 444 to 111. Now we have here recorded route option. Okay, then this third, fourth, fifth, this is another great use of extended ping command, right? So I believe it has been information for you. Okay, so thank you.